This video is a continuation. So this is a continuation of chapter 1. So we're going to pick up with accuracy, precision, and significant figures. So continuing your, excuse me, chapter 1 videos. So let's start out with accuracy and precision of a measurement. Most of us use accuracy and precision interchangeably, and they shouldn't be used that way. So accuracy is how close a measurement is to the correct value, and precision is how close your measurements agree with each other. They could all be really wrong, but agree very closely with each other, and you would be precise, but you wouldn't be accurate. So let's look at the example. A ruler is 12 inches long. You measure it with a tape measure and get 12.2 inches. You've got a friend, your friend gets 12.4. You are more accurate because you're closest to the correct value. So let's take the ruler and measure again. So now I'm going to measure it and I get 12.5, 12.4, 12.5, and 12.5 inches. And then my friend comes in, and my friend gets 12.0, 12.3, 11.9, 12.1. So I am more precise. My measurements agree with each other very closely, but I'm not at all accurate. My friend is not as precise. He has a swing of 0.4 inches in his measurements from the largest to the smallest, but his numbers are all closer to the actual value. So I am more precise, but he is more accurate. The goal, of course, is to be both precise and accurate. So for homework, we've got an example with two groups. We want to know, are they precise or are they accurate, or are they both, or are they neither? I suppose you could be neither. So you'll want to work on this just to make sure you have a grasp of it, because usually I offer some sort of quiz question related to this. So let's look at uncertainty. Some of you have had chemistry and are really good with it in that respect, especially with significant figures. We're going to do it a little differently in physics, so bear with me. So most of the time, our measurements are imprecise because of the limits on our measuring device or because of the limits on the person doing the measuring. And if you were working in industry, you might need to include some estimate of uncertainty. We are not going to do it in lab. We have other lessons to learn, but I want you to know where these numbers come from. So let's look at them and what they mean. So in our example, we have the number 2.78, and then we write it as plus or minus 0.03 grams. What that tells me is that I think my number is 2.78. That's what I measured. But my confidence in my measurement is it could be as much as 0.03 grams larger than that, so 2.81 grams, or as much as 0.03 grams smaller, so 2.75 grams. So we have a range of values. Obviously, we'd prefer to have our range very narrow, but that's not always the case. Now, sometimes you don't want a numeric range, you want a percent uncertainty. So to calculate that, you take the uncertainty, so in this case, the 0.03 grams, and divide it by your measured value, in this case, the 2.78 grams. Take the decimal number that you get and multiply it by 100 and tack on a percentage to use for the unit. So let's do that example. We want to find the percent uncertainty in 2.78 grams plus or minus 0.03 grams. So first of all, we always write down our formula. Every calculation you start for me, you'll start by writing down the formula, and then we plug into it. So uncertainty was 0.03 grams, measured value is 2.78 grams. The grams cancel. 0.03 divided by 2.78 gives me 0.01079. Multiply that by 100. I know I've written down the percent. If your calculator has a percent button, don't use it. So taking a number and multiplying it by 100 turns it into a percentage if your number's calculated in this way. So we would have 1.08%. Again, don't use the percent button on your calculator. If the uncertainty is not specified, we assume that we're accurate to plus or minus 1 and the last number you wrote. So we have 52 grams, it's 52 plus or minus 1 gram. And here are some practice problems again from the end of the chapter involving percent uncertainty. Let's talk about how we calculate uncertainties in a calculation. Again, not just in a measurement, but in an actual calculation, because physics has lots and lots of calculations. So one way is to use the method of adding percents. You take those percent uncertainties that in a quantity that's been calculated by multiplying or dividing, then you take the sum of those percent uncertainties and that'll give you the percent uncertainty for the value itself. And I know that seems a little confusing, so we'll just do a numeric example. So we want to calculate the velocity of a car. The car travels 5 meters plus or minus 0.1 meter. So that's 5 meters plus or minus 2%. I went ahead and did that. The time it takes it is 10 seconds plus or minus 1/10 of a second. So 10 seconds plus or minus 1%. And now we want to calculate the velocity, and then we'll calculate its uncertainty, its percent uncertainty for the velocity. These first two, distance and time, are for measured values. So velocity has an equation. It's distance divided by time. We will get to that in a later chapter. So we write down our formula. Velocity is x over t, x for distance, t for time. In physics, we almost never use x to indicate multiplication, except when it's a number written in scientific notation. We almost always use it to represent a distance. And lowercase t is almost always time. So if we know that distance is 5 meters and time is 10 seconds, we plug them in. So 5 meters over 10 seconds is 0.5 meters per second. So that's my velocity. In order to get plus or minus what percentage we've got, where did I get that 3% from? Well, the distance was 2%, the time was 1%, 2 plus 1 gives me 3%. This is the method of adding percents because we had to divide two numbers to get an answer. If we had multiplied two numbers, we'd still add the percents. So again, 2% plus 1% gives us the 3%. And we can calculate that 3% of 0.5 meters per second is 0.015 meters per second. We are actually not going to do this. I wanted you to see an example so you'd understand what we meant. You're not going to be expected to do it. You're expected to know when it's used. So adding percents is used when you multiply or divide numbers to get an answer, but we're not actually going to do it. And again, this just shows you where I got the 0.015 meters per second. So 0.5 meters times 3% is 0.5 meters per second times 0.03. Notice for multiplying, we put numbers in parentheses. We don't use x's. And that's where the 0.015 meters per second came from. So let's look at significant figures. The number of reliably known significant figures gives us the number of significant figures, the number of reliably known digits in a number gives us the number of significant figures, and it's not the same thing as the uncertainty or the accuracy. So if we write a number as like 1.95, we've written down 3 non-zero digits, they are all significant, so it's got 3 significant figures. The number 0.4507. We don't count the leading 0. We always start with the first non-zero number. So here's the 4. So we've got the 4 and the 5. The 0 is followed by a non-zero number, so the 0 counts. So the 4, the 5, the 0, and the 7, we have 4 significant figures. Zeros can be tricky. We've already found out I don't count it if it starts the number. And there are times when you don't count it at the end either. So a 0 at the end of a number only counts if there's a decimal point. So 250 without a decimal, the 0 doesn't count, it has 2 sig figs. 2000 without a decimal only has 1 sig fig. Suppose we have a 0 at the start of a number. Well, there's a 0 and a decimal and 2 more zeros. None of those zeros start. We start counting our significant figures with the first non-zero digit. So this number only has 2 sig figs. A 0 that follows a non-zero in a number with a decimal is always significant. So here's a decimal, there's a decimal. They didn't have to lead with zeros, but I chose to do that. So first non-zero digit is the 4. Here's a 0. It's followed by a non-zero. So these 3, 4, 0, 5, all count. Here is a 0, decimal 0. They don't count. Here's the first non-zero, the 2. The 0, it counts because it's followed by a non-zero. And here is another 0. It actually counts because of the placement of the decimal. So any 0 that follows a non-zero number, a non-zero digit, in a number written with a decimal counts. So the 2, the 0, the 3, the 0, they count because of that decimal and the fact that these 2 zeros follow a non-zero number. So zeros banked on either side by non-zero numbers, they count. So 2305, the 0 counts because it's got a non-zero number on each side of it. 4050, the 4 counts, the 0 counts, the 5 counts. The last 0 does not because there's no decimal and there's not another non-zero digit. So this one only has 3 digits that count, 3 sig figs. I know, it's terrible. So there are some examples in the book about check your understanding. So let's look at what happens when we add, subtract, multiply, or divide numbers. So adding or subtracting, you want to keep to the least accurate value. So let's look at our example. 1.75, accurate to the 1/100th place, that's where the 5 is. 2.0, accurate to the 1/10th place, that's where the 0 is. 3, accurate to the 1's place. So add those up, we get 6.75. We have to keep to the least accurate value, that would be the 3. Not the least number of significant figures, but the least accurate value. So to the 1's place. So if you round off 6.75 to the 1's place, it's 7. Multiplication and division, keep to the smallest number of significant figures. So 2.0 multiplied by 3.75 gives us 7.50. The 2.0 has 2 sig figs, the 3.75 has 3. Our answer can only have 2 sig figs, so 7.5. Now, I'm not going to be a stickler for that unless I say write it to the correct number of significant figures. Because most of the time we're just so knee-deep in a calculation. We have other things to worry about. I just don't want you to round off too much too soon. A number like pi, 3.14159, ... is considered to have an unlimited number of significant figures, so you can't use it, or a formula like the radius is equal to the diameter divided by 2. The 2 in that equation has an unlimited number of significant figures. There are more examples in the book. You should look at them. Always best to write our answers in scientific notation if you have to care about the number of significant figures. So 2.00 times 10 squared, not 2 times 10 squared, because of that decimal. And we have some homework problems to look at. Again, just practice with this. So here is a table from the book. Again, metric prefixes, the abbreviation, and their values. I will introduce them as we use them, but I wanted you to know where they were. And that stops chapter 1.